How do we count atoms? We use the mass of the atoms to count them. They're too small, too numerous to count individually. Oh, here's the analogy. Even if you could see atoms and counted them 24 hours a day, as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand. For the rest of your life, nonstop. Nobody's going to do that. So dozen was really convenient for the nails, right? And it's convenient for lots of things in everyday life. But it's too small for atoms because there's just so stinking many of them. And it's too small for some things in everyday life, too. You don't buy a dozen sheets of paper or 5 dozen sheets of paper. What's the unit they use to sell paper? A ream. A ream of paper is 500 sheets of paper. Another unit that's a counting unit is a gross. A gross is a dozen. So it's 144 things is one gross. So you might have a gross of bottles or something. Chemists have a larger unit that's similar to a dozen. It's called a mole. M-O-L-E. Not a sauce, not a little nearsighted animal. Mole. It has an abbreviation, MOL. I think that's stupid, but there it is. Everybody else does it. So we call this a chemist's dozen. A dozen is 12 things. A mole is a few more than 12. 6.022 times 10 to the 23rd things. Could be atoms, could be molecules, could be people. They wouldn't fit on the planet, but it could be people. You could have a mole of things, right? It's a counting number just like dozen or ream. This number, 6.022 times 10 to the 23rd, is called Avogadro's number, named after the scientist Amadeo Avogadro, 1776 to 1856. He did some really cool experiments that led us to the understanding of what that number was, or is. So that's 1 mole. Why is it that number? Well, it was chosen to make things simpler and to be a reasonable quantity of stuff. So this is a mole of copper atoms. You could hold those pennies in your hand. It's big enough that you can see it and do something with it, but it's not so huge that you can't carry it around the lab. So a mole is a useful number of atoms. It's a reasonable quantity. 2 helium balloons is about a mole of helium atoms. So a mole of a substance is a useful amount of it. Reasonable size. That number came from the definition of the atomic mass unit, kind of indirectly. So they define the numerical value of that as being equal to the number of atoms in exactly 12 grams of pure carbon-12. Now we know what carbon-12 signifies, right? That's a carbon atom with a mass number of 12. 6 protons, 6 neutrons. Mass number of 12. It's the most common carbon isotope. So a mole of carbon-12 atoms weighs exactly 12 grams. They started actually using the concept of a mole before they knew what the number was. They said, well, carbon-12, 12 grams of it, we're going to call that a mole. So this gives us a relationship between the mass of carbon and the number of carbon atoms. And it allows us to count atoms by weighing them. So it's analogous to a dozen nails weighs 0.16 or 15 pounds, whatever it was in that example. A mass related to a counting number of objects. 1 mole of atoms is equal to this many atoms, just like a dozen nails is equal to 12 nails. So if we have this number of atoms and we want to figure out how many moles of atoms that is, we use this as a conversion factor. So 9.5 times 10 to the 27 atoms. I want to find out how many moles. So I'm going to put moles on the top and atoms on the bottom. So the units cancel out. Dimensional analysis again. 1 mole is the number of atoms. Just like it would be silly to say that 12 dozen is equal to 1 nail, it's very silly to say that 1 atom is equal to 6.022 times 10 to the 23rd moles. That's backwards. So then you do the math. This number is one of the reasons you have to know how to use scientific notation on your calculator. I have not yet seen a calculator that would allow me to enter that number in decimal form. That's a 6 with 23 zeros after it. That's huge. So we do this problem by entering 9.5 EE, standing for times 10 to the 27, and then divide by 6.022 EE 23 equals. And so I'm getting 15775.48987. Anybody else get that? The unit is moles. How many sig figs? 2. This number had 2. In scientific notation, it's just however many digits are over here. This is placeholding. This number is known to more significant figures, but since we don't really need that amount of precision, this is what we're going to use. So this has 4 sig figs, not an exact number. 4 sig figs, 2 sig figs, 2 sig figs is smaller. So I want to keep the 1 and the 5. Do I round this to 16 moles? No. Because that would be a little different than 15,775 moles. So anytime you're rounding to something that's to the left of the ones place, be really careful that you don't change the number. You can take this 5 and see that there's a 7, I need to round it up. Okay, 1, 6. And then I have to replace those digits with zeros. If you can do that, that's great. Some people have a hard time with that, so then use scientific notation. Scientific notation, I want to keep the first 2, so 1.5, but the next one's a 7. Did not mean to do that. So I want to, I have to round that up. And there's my 2 significant figures. And then I can just stop and write times 10 to the. And when I'm doing scientific notation, I'm figuring out this decimal point. The decimal point was here. I want it to be after the 1. I want it to be over here. How many places did I move it? 1, 2, 3, 4 places. The exponent is a 4. And then I need to decide on the sign. Is this a big number? 15,000? Yeah, big number. I have positive feelings about big paychecks, so the exponent should be positive. And the unit is mole, and there's my best answer right there. Any questions? That's what we got. So how many gold atoms are in a pure gold ring that has 8.83 times 10 to the minus 2 moles of gold? Well, I only have one number, so that has to be what I'm starting with. So 8.83 times 10 to the minus 2 moles. And what is it asking me to find? Atoms. So I need to go from moles to atoms. Do I know a relationship between moles and atoms? It's Avogadro's number. So it's like going from dozen to a number of things. So I can do this in one step. 8.83 times 10 to the minus 2 moles times and a number. Moles to atoms. Atoms go on top. Moles go on the bottom. The moles will cancel. The relationship between atoms and moles is like the relationship between eggs and dozens of eggs. A dozen eggs is 12 eggs. A mole of atoms is Avogadro's number, 6.022 times 10 to the 23rd. So I've got 8.83 EE minus 2 times 6.022 EE 23 equals looking at my starting number, this should have 3 sig figs, 5.31, that's my third sig fig, 74 times 10 to the 22 atoms. And rounding that will give me 5.32 times 10 to the 22 atoms. That's a really big number. Is that okay? Yeah, it's a gold ring. This is something that's large enough to see. Anything that's large enough to see is going to have a ginormous number of atoms in it. Any questions?